issues, challenges, and solutions in both centralized machine learning and federated machine learning. So the motivation is that we all know that ML models, DL models, and AI has been used in across the domains, even including the sensitive domains like healthcare and finance. But at the same time, they are prone to biases leading to unfair decisions. And all of us have heard about the LLMs like ChatGPT generating some hallucinations or generating some biased results, like which might be due to the more data is coming from the West countries. Like most of the results generated by ChatGPT is in the context of US, but not in the context of, like, if you search for the Southeast Asia or any other country. So AI can easily go into other direction, and it can exaggerate existing bias, creating cycles that reinforce, that can cause bad algorithms to give biased credit allocation and result in discrimination on the basis of some sensitive attribute, be it gender, be it nativity, or be it color. This problem has been investigated since it has a long history. Like it's not only AI, the humans are also biased, right? So there has been existing rules in US, like Equal Credit Opportunity Act, Truth in Lending Act, Fair Housing Act, but these all are quite old acts, and they were supposed to be fair. Like a human is sitting there deciding the outcome, but he or she has to follow those rules and try to be fair while allocating any welfare schemes, or while allocating credits, mortgage, and all. However, these existing rules are based on a time and we have exactly opposite problems now, what we face now. So there is a need to improve and fix the fairness and biasness problem in existing machine learning settings. Moreover, there are certain regulations in every country which doesn't allow you to gather information from the participants, like in GDPR in Europe or HIPAA in US doesn't allow to collect some sensitive information. So even if those sensitive informations are not taken, like even if gender is not taken, even if nativity is not taken, even if race is not taken into account while deciding credit or mortgage, but there exist proxy attributes to that, like we see in a machine learning model. When we design, there are many attributes. So even if we remove the sensitive attributes, there are many proxy attributes, like which has a high correlation with the sensitive attribute, like based on which movie you watch, on which deodorant you buy, you may easily decide that whether that particular sample or that particular data subject is male or female, right? So it's not that easy that even removing the sensitive attribute, you can the machine learning model will act fairly. There are some recent news in recent, like 2024 news, the last news. AI system used by UK government to detect welfare fraud was showing bias based on people's age, disability, marital status, and nationality. So when we tell that a system should be fair, then what is the expectation from the system? That we'll learn later, that the system should behave fairly. It should give equal opportunity to samples irrespective of any sensitive attribute. Like it should not be decided that whether the person is male or female when allocating the mortgage. It should be decided based on the other factors. But still, there is a famous incident reported in Amazon, that when Amazon shortlists the resume for hiring, it by default prefers men over women. So it's not intentional bias. It's the bias is because they have an historical bias. Like the most of the resumes are of male, or the history, the data collected in the last 10 or 20 years belongs to more male. So that induces bias in the system, in the machine learning setting, and that results in an unintentional bias in the machine learning model. There are the other examples in US reported here. So when we are trying to incorporate AI into any sensitive system, be it finance or be it healthcare, there exists a trade-off. Like even if you are going to mitigate bias, it it has a trade-off with accuracy. We lose some accuracy when we are trying to achieve some more fair system, like having low. There are some matrices like equalized opportunity, demographic parity to measure bias, and these are based on probability. So when we try to minimize these things like demographic parity or equalized dots, at the same time we lose some accuracy, and that's why there exists a trade-off between them. What is the origin of bias? So the bias may be due to the sampling bias, like when we are collecting data, there are some overrepresented group, there are some underrepresented groups. So that itself, like if in our training data there are 80% male and 20% female, by default male will become a prominent attribute in the machine learning classification problem or whatever problem it is. The another is labeling bias, like an example of this would be like labeling a loan applicant occupation as doctor versus nurse rather than healthcare worker. So it has been a problem investigated in computer vision long back that if a lady is wearing white dress, by default it is understood that she's a nurse. So can we label it like it that should not be a huge concern that the lady is nurse or doctor when giving a mortgage, rather her repaying capacity, rather her other factors will be the major concerns rather than being labeled as doctor or nurse. So can we label it as a healthcare worker? But even labeling correctly doesn't guarantee that it will mask the gender, right? Because doctor and nurse, uh, they might be correlated with some other attributes, and that will result in revealing their gender. And the third is the outcome proxy bias. When the machine learning model, the algorithm is itself poorly defined, it is itself as like we are solving some complex task and we are still solving it with some linear algorithm, so it will fail. There are several phases of bias mitigation. It can be pre-processing. So before the data, before even the algorithm has been trained, so we try to clean the data, we try to remove the proxy attribute, we try to remove or mask the sensitive attribute as much we can. So that's called pre-processing of data. And that's called pre-processing bias mitigation phase also. In processing, when the time you are training the model, at the same time we try to we apply cross validation and we apply testing a strategy and all to check that whether the model is behaving have good accuracy or not, right? So at the same time we need to check that whether it has good fairness or not, and fix at the time the model is getting trained. But the most of the machine learning models are investigated in post processing phase for bias mitigation. So that becomes quite challenging because you have already the trained model, and now you need to fix the bias. And you don't have access to the private training data. We can visualize a situation like a bank is facing a bias issue, and banks, even the most resourceful banks like say like HSBC, have not are not well equipped at this moment that they have in-house solutions to fix this thing. So what they rely on, whom they rely on, third parties. So they need to expose their model to mitigate that bias, but they don't want to because that will lead to another repercussions. So there is so this is the most studied bias mitigation phase where we try to reduce the bias after the model is already in the market or already in the production. These are the fairness criteria. So fairness can be mm, can be talked in terms of group fairness and individual fairness. So when we talk about individual fairness, we tell that the the third one, the sufficiency. So it tells that the likelihood that an individual belonging to a positive class, classified positive, should be same for both sensitive groups. So here we talk fairness in terms of a particular individual, but in this talk we will mostly consider about group fairness. So when we talk about group fairness, we consider that a male, like let's assume the sensitive attribute is gender, then a male should have equal opportunity for anything, like be it mortgage lending, compared to female if all the other attributes are same, right? So there are two well-known matrices. One is demographic parity and other is equalized dots. So how we evaluate demographic parity. So demographic parity, we define it as that probability to be classified as good or positive should be same in both groups. So the probability to classify to get a loan given a male should be equal to probability of getting a loan given a female, should be equal. We are not talking here about the case where loan is not given based on any criteria like credit score is low or whatever. We are not considered about negative case here. We are only considering the positive case here, that probability to be given loan given the person is male should be equal to the probability of sanctioning loan given the person is female. So what we want, that this probability should be equal or closer to each other, right? So so if the subtraction of both is closer to 0, it means lower is the discrimination. However, this has its own repercussions, which we'll talk in the next slide. So the next attribute is separation, which is also known as equalized odds. So we define it as the classification based on predicted scores should be independent on the group. Like here we consider both false negative rate and false positive rate. So the equalized odds tells that the probability of getting false negative and false positive should be same for both male and female, given that gender is the sensitive attribute. So what are the issues in with using demographic parity? So for example, the problem with this approach is that like you are trying to make the probability of giving loans same for both male and female, but it has been found that most of the female samples, female test cases, or the person with female gender has not a good credit score. Then what will happen? In this case, members of both groups have the same probability of receiving a loan, where one group will experience more actual defaults. So it will cause more defaults. So to fix this, separation can be used. So it addresses the dilemma posed by the independence criteria and acknowledges that a sensitive attribute might correlate with different default rates. However, it might be inadequate if credit scoring had a strictly preferred outcome for a customer. Like in US, there has been quite many cases of biasness for white and black. So there are some banks only made for or only meant for black people, where they get loans even if they are not fulfilling the criteria in other banks. So this separation criteria will be inadequate if the credit scoring has a strictly preferred outcome for a customer. So now we talked about the issues and talked about some bias mitigation phases in centralized machine learning setting. Now I will jump that how FL federated learning comes into picture, how it can solve some of the issues, how it brings other issues. And any questions till now, or should I proceed next? Okay, so I will briefly talk in 1-2 slides about FL, but before FL, like we all know that FL is a collaborative machine learning system that is also supposed to be privacy preserving, and where participants across the demographics have their own data, and they train their local models. They train local models over their local private training data, share the model. But the studies tells that even when in collaboration, the local participants propagate bias to the global model. So just a brief recap of federated learning is that it executes in 5 steps. Like the local participants compute their local updates locally. These updates are sent to the server. The server aggregates it, does the aggregation using federated average or any other aggregation mechanism. It's sent back to the clients, and it gets repeated until the convergence is achieved. And each participant trains the model in place with some random samples chosen in every iteration, and the central aggregated sums up, like in the equation shown like the W in iteration t plus 1 will be the average of the gradients received in that particular iteration. Okay, so now let's see what can be the use case with federated learning and what can be the problem when we are using FL. So how a bank in Africa can benefit collaborating with a bank in UK. So it can be that the African bank has a bias in loan approvals due to limited historical data to female entrepreneurs. So by collaborating with the UK bank, which may have a more diverse data set, the African bank can improve its model to provide more. So like UK, we are assuming that the UK bank has more fair data set for male and female entrepreneurs, while the African bank itself doesn't have sufficient data for that. So when these two collaborate, African bank will be able to develop a more equitable loan approval system. However, at the same time, the African bank would like to continue its lending strategy because the income range might be different and will be different in UK and Africa, right? So at the same time, when these two banks are collaborating, they want to learn something, but they don't want to learn everything and get influenced and biased by that, and which could cause the loan approval system more worse, which will make that more worse. So we want to remove the bias over that particular sensitive attribute, but it shouldn't cause the problem to the general lending strategy of African banks. So here we want to achieve two things: fairness plus personalization. So there may be two primary cases. There might be more, that if both the participant banks have same bias, like let's assume that banks across Africa are collaborating. So if both banks have the same bias in their data sets, the bias will persist and will be amplified in the final global model, right? Like both the banks A and B in Africa are biased towards female entrepreneurs. Then when they will collaborate, the global model will have amplified bias. So when we do aggregation here, the bias should be mitigated locally. So why I'm talking this? Because the bias may be good or bad. So it's contradictory, like how a bias can be good. So the point is that, as we learned earlier, that mitigating bias has also effect and a trade-off with accuracy. So in case 2, if both the participant banks have different bias, like bank 1 is positively biased towards women, giving them higher credit scores than they deserve, bank 2 is negatively biased against women. So when these two banks will collaborate, having positive and negative bias, when they will collaborate, we don't need to mitigate the local bias locally. It will automatically get mitigated, and at the same time, since we have not applied local mitigation strategy, it will not have an impact over the accuracy. So that's why we call that, is local bias good or bad? Should we remove it locally or not? It is a research question, and that's what people are currently working on. Like there are some recent papers in 2023 and 2024 working in this area, and I have submitted a paper for review in this area itself. So I'll briefly talk about that paper. Yeah, I can talk a bit about the paper that we have submitted and what it tried to achieve, and how it tries to have fairness aware aggregation in federated learning settings. So our algorithm works in 3 steps. So in step 1, in this picture we can see that there are three institutions, but let's assume there are n institutions, 1, 2, 3, 4, and n institution means n participants across demographics. So in step 1, all the participating institutions or the clients will train over their locally held data set, as we do in FL, right? Then they will perform fairness constant optimization, which considers to minimize both training and fairness loss. So when we train a machine learning model, we optimize the training loss, right? We do the back propagation and try to minimize the loss, right? But at the same time, here the institutions are trying to minimize both training loss and fairness loss. So fairness loss will be defined separately, and in 2018 a paper defined fairness loss, because to optimize loss, it must be differentiable function. So demographic parity and equalized odds, when you will calculate it, it will be a scalar things. So we cannot differentiate a scalar, right? It's constant. So first we need to approximate it in a function which becomes differentiable, and then we can optimize both training and fairness loss together. Then the clients use the model interpretation technique to identify the responsible model weights causing bias and misclassification. So even after doing a step 1A and 1B, it is not guaranteed that the model will act fairly and accurately. So what we will do, we will identify the responsible model weights from the trend local model responsible for bias and misclassification. So here we are giving marking two terms, bias and misclassification. So both have their importance. Like when we try to even fix bias, like sometimes we can achieve good statistical parity, but at the same time it induces more misclassification in the model. I will talk a little bit more about it in the next slides. And model interpretation is nothing but it is a kind like we interpret it. It is a kind of explainability technique that we might have heard about Shapley value, where we think that which particular feature is important for this classification problem. Similarly, we can use this model interpretation technique to find that which particular model weight is responsible for causing this bias. In a step 2, so in a step 2, the clients need to communicate with each other, right? And since FL promises to be privacy preserving, we cannot simply, each participant cannot tell that I have this bias, I have this bias, I have this data statistics. They can tell. So they need to talk privately. So all clients share the indices of their most responsible weights for bias and misclassification to calculate the frequency of such weights across the clients, which helps all the clients to calculate their own individual aggregation weightage. So when I tell aggregation weightage, so in federated averaging, in the simple averaging used by federated learning, we simply average the local models received. But simply averaging means giving same weight to everybody, right? So if we will do this, we will not be able to fix the bias. So we need to find different aggregation weightage for different participants, and that too based on how much bias they propagate and how much misclassification they are inducing. But to calculate this weight, the server need to know that how the data is distributed across the participants, right? Then it will decide that okay, participant 1, even if it has bias, it doesn't need to punish or penalize. So and in step 2B, they calculate the sum of the individual aggregation weightage, which further helps in calculating the final average aggregation weightage. And these operations are executed either using secure aggregation or homomorphic encryption, such that it doesn't lose any private information about any particular institution, because biasness has also some relation with privacy attacks. The more a model is biased, it is more prone to privacy attacks, because if somebody knows, if the attacker knows that the model is biased towards male, it will easily be able to learn more information. It will be able to, the attacker will be able to frame such attacks and learn more information from the model itself, only from the model which is released, by just putting some black box only query only access only. Yeah. So the step 2, like sharing the data statistics with the server, should not be done in plain text. It is also compatible with the proposed protocol is compatible with like secure aggregation using SMPC or homomorphic encryption. In a step 3, the client do secure aggregation to calculate the final global model, which achieves both balanced accuracy and fairness. So we talked about the term bias and misclassification earlier, and I mentioned that they both are important. So what is accuracy and what is balanced accuracy? So let's assume an example where a binary classification model which always predicts positive. Then what happens that if 90%, given that 90% samples are from positive class and 10% are from negative class, the accuracy will be 90%, which is high. So we will think that it's a good accuracy. The demographic parity is 0 because the probability of predicting positive is same for both, because the model is always predicting positive. So the demographic parity is also 0. So we can mark that the model has good accuracy and model looks fair. But is the model fair? No, because even all the samples from negative class are getting classified positive, right? So the balanced accuracy is 50% here. So this particular problem is called misclassification problem. So fair trade paper in III 2024 showed empirically that existing state-of-the-art debiasing techniques minimize the discrimination or mitigate the bias at the cost of balanced accuracy. Uh, Now I will go in the details of the algorithm. I will go a bit fast here. So in step one, uh, all the local participants do local model training, just like simple FL. However, this doesn't guarantee that the aggregation of these local models will result in a fair global model. So in step 1B, all the participants identify the responsible weights using model interpretation technique like Shapley value, that which particular weights in this model are responsible for bias or misclassification. So how we do this? So let's assume xs is a sensitive attribute with two groups s and s prime. So we will collect some samples, TPS. These are the positive samples with S. For simplicity or for understanding this intuition, let's consider the sensitive attribute at gender again. S be male and S prime be female. So true positive S, like the positive samples with sensitive attribute male are classified as positive. So these are good case. FNS, false negative. So positive samples with female but classified as negative. Similarly, we take some samples TPS. So positive samples with S prime means positive samples with female and also classified as positive, and false positive S prime. So negative samples with S prime but classified positive. So we can calculate the responsible weights causing bias from samples 1 and 2, because in samples 1 and 2 we wanted the positive samples with S prime to be also classified as positive. So we will take help of the samples from 1 and 2 to calculate the model weights responsible for bias. While in 3 and 4, these particular samples can be used to detect the model weights responsible for misclassification, and we use this particular technique to identify the model weights responsible for bias. So what we do, that we give both data samples from both sensitive attributes D and D prime. So D represents the data set of male and D prime represents the data set of female. We find the weight importance. So when we give D, we can find the weight importance of each weight, like we can find the importance of each weight in the model for the classification. So one in green color represents for female, and one in the little bit whatever color it is, it represents the weight importance due to male. And when we subtract the weight importance between these two, and where there are the highest gap, it tells that that particular model weight was responsible for the bias or responsible for the misclassification. So what we do, that we identify the model weights with widest weight importance gap, and those particular weights we term as responsible weights for bias and misclassification. And we use the concept of Shapley value, but if you are aware about the concept of Shapley value, it is quite expensive, and if you try to run it on a model of parameters 10 to the power 7, 10 to the power 8, 10 to the power 9, it's infeasible. So we need to approximate it, and we need to apply random subsampling method. And we have published this paper already in Nikai, so it can be referred from there, that how we can do random subsampling to identify model weights and weight importance on a big model, on a larger scale model. And then we go to the step 2, where the participants, all the participants communicate with each other and share their data statistics of the responsible weights. And just for an example, like let's assume that there are 3 participants for simplicity, and their responsible weights like in and we are considering the model of very small size, only of 4 parameters for simplicity, for just illustrating this example. So in model 1, the only fourth parameter is responsible for bias. In model 2, second and fourth are responsible for bias. In model 3, second, third, and fourth are responsible for bias. So the intuition is that the idea is that to penalize a weight strictly if it is responsible for causing bias in more local models, right? So that's the intuition. So we share that statistics either using SMPC or homomorphic encryption to the central server. The central server calculates the sum of all those responsible weights which are in binary. So and we call it as a frequency. So a frequency closer to the number of clients signifies that weight is causing bias in majority of the models, right? So if frequency is 3, means that particular model weight is causing bias in all the models. So it needs to be punished strictly. And if the frequency is closer to 0, it means that particular weight is not causing bias in majority of the models and should not be punished. And then we find the aggregation weightage scoring by this formula n minus frequency into the weight at that indices divided by the number of participants. And we introduced two hyperparameters, beta 1 and beta 2. So beta 1 can be any real number in 1 n divided by n minus 1, because a larger number from this range will assign a weightage score greater than 1 to a weight causing bias, and beta 2 can be any real number greater than or equal to 1, because they help decrease the weightage score for the responsible weights for bias. Yeah, and then we can simply, these steps are very much compatible with homomorphic encryption, because homomorphic encryption allows addition and multiplication, and that's why it's allowed that the local participants in the FL cycle can share their statistics by encrypting with a public key, and those operations are allowed. Homomorphic operations are allowed at the server, and the server return back those aggregation weightage score to the clients, and then the clients can decrypt it. Now it depends on that how much computationally expensive equipped the clients are. So based on that, they can use single public key or single public key, single secret key setting, or single public key and threshold decryption, because if you are using single public key and single secret key, then any participant can decrypt the aggregation weightage for any other participant. So if threshold decryption is allowed, we can adopt that. That's out of the scope for this work, but it is compatible to this work. This is the algorithm that just summarizes what we discussed, and we evaluated it over some datasets like adult dataset, bank dataset, default law, and KDD dataset, and compared against with some existing fairness aware aggregation methods. We were able to achieve better result in 3 of the datasets and comparable result in 1 and 2. We investigated that why it is not behaving quite well on adult and KDD dataset. So the adult dataset causes poor global model accuracy itself. So we were not. So our proposed approach was not able to work well over that. And KDD has an almost balanced distribution among the two groups of sensitive attributes, and already carries very little bias. As a future scope, like we just talked that here we just talk how we can mitigate bias and misclassification, but we didn't talk about personalization. Like in the use case, we talked that when African bank is collaborating with UK bank, it wants to learn, it wants to mitigate bias, but at the same time, it doesn't want to impact its lending strategy over lower income individuals. So that requires personalization to be adopted and locally. Yeah. So this work can be extended like this. And okay, thank you. Any questions? Hello. Am I
Yeah, yeah, audible, Dr. Kashyap.
Yeah.
Yeah. So it was a very nice presentation. You actually told about in depth about how these things in the banking application, how these federated learning you are using it. Um, we really thank you for sharing your knowledge in this particular field. Thank you so much, Sean.
Thank you.
I hope it was very clear what you are telling. I think there are no questions from
Sure,
anyone. Anyway, yeah, we'll just close the session. Thank you everyone
sure,
for
sure.
the session.
Thank you.